Okay, good evening, everybody. I'm Greg, WA1JXR. I was asked by George, who coordinates our stuff, to do a presentation this evening on end-fed half-wave antennas. I guess there's some interest in that. So I had this presentation that I had done. I did it for the Ham Expo, I think, and QSO today. So I've done it a couple of times. So hopefully you'll enjoy it. So, end-fed half-wave antenna in the HOA. Um, we all know that a wire antenna, once you get a wire antenna up, it's pretty much invisible, hard to see. And the problem with the old faithful center-fed half-wave dipole is you've got that, feed line coming down from the middle, which is a dead giveaway, right? Well, the end-fed half-wave antenna kind of solves that because now the feed line is at the end and you can hide that in a tree or up against your building or somewhere. It's not as obvious. You just have that thin wire going out. Um, and you'll just need a small 49-to-1 transformer at the end of the wire in order to make it work with the 50 ohm coax. Of course, the center fed dipole has been around for, forever. And it's a great antenna because you take two pieces of wire, split it in the middle, hook your coax up. You don't even need a balun, and boom, you're right on the air. It's a great, efficient antenna. It works really well. But one of the disadvantages that you'll see that you get with the end-fed half-wave is the center-fed dipole is basically a single band and antenna. Yeah, you can get it to work on the third harmonic, like a 40-meter dipole will work on 15, but it's not really meant to do that. But the end-fed half-wave is actually a multi-band antenna, so that's another advantage you get with a single wire. You basically get all the HF bands, and they're both dipoles. They're both half-wave dipoles, so the antenna patterns, the gain, everything is identical between the center-fed half-wave dipole and the end-fed. So basically, it's a half-wave resonant antenna at the lowest frequency, depending on what your length is. And here's, three of the most common lengths that are used, either the 135 foot, 66 foot, or 33 foot, depending. Uh, but these are all the bands that the antenna covers. It's pretty much, you put the 80-meter one up, and you pretty much got all the bands there. And like we said, it's fed at the end versus the middle. And one of the disadvantages of feeding it at the end is the impedance at the end of the half wave wire is very high. It's like 2,500 ohms. So hooking a 50 ohm coax up without anything is not it's not going to work. You need the 49-to-1 transformer to transform the impedance. Because if you take 2,500 ohms and divide it by 49, you get very close to 50. So let's take a look at how that really all works. And this diagram kind of tells everything. So here we have a diagram of a half wave dipole. And you remember a full wavelength is 360 degrees. So you see along the bottom of this graph, 180 degrees. So that's a half wavelength. And we have a couple curves on there. The blue curve is the current distribution across the half wavelength wire. It's maximum in the middle and it's zero at the ends. And the green trace you see is the voltage distribution across the half wave wire. It's zero in the middle and maximum at the ends. So if we look at that middle red line, where I've drawn that red line that's where the center fed point would be for a half wave dipole. And if we remember down at the bottom of the chart here, you see impedance is the voltage divided by the current. So if you take the center fed dipole, we have a situation where the voltage is low and the current is high. And if you do that voltage divided by current, you have a low number divided by a high number. That gives you a low number. And that's why the impedance at the center of the half wave dipole is a low number. It's 50 to 70 ohms. It varies slightly with height above ground, but that's what makes the half wave dipole. You take your coax, wire it right up to the dipole. You don't even need a balun, and it just works because you have a good power transfer between the feed line and the antenna. Some alternates to the center fed is off center fed dipole, OCFD, and you see that one just to the left of the center there at the 60-degree point. And that's where instead of breaking the wire at the middle, you break it at kind of a 1/3, 2/3 point. And if you look at the voltage and current at that point, you kind of have a mid-range voltage and a mid-range current, and you do that voltage divided by the current, look at the impedance, and it's a mid-range impedance. It's in the 200 to 300 ohm range at that point. And so with the off-center fed dipole, what you use is a 4-to-1 balun. Takes that 200 to 300 ohms, divides it by 4, and gets you down into the 50 ohm range. And that's how the off-center fed dipoles work. If we now look at the very end, the 0-degree point there, that's where we're trying to feed the end-fed half wave. And you see we have a very high voltage divided by a very low current. A high number divided by a very small number gives you a high number, and that's why the impedance at the end of the wire is 2,000 to 3,000 ohm range. Any questions on that? So now if we take a look, and instead of feeding this antenna with the fundamental, we now feed it with the second harmonic. This is what the voltage and current distribution now looks like, right? You see two humps of those current and voltage waveforms. But the thing to notice is at the very end of the wire, it looks exactly the same as it did for the fundamental. You have a high voltage and a low current. And guess what? At the second harmonic, you get exactly the same impedance, that 2,000 to 3,000 ohms at the end of the wire. All of a sudden, it works on the second harmonic as well. Third harmonic. Anything look familiar about the end of that? It looks exactly the same as the fundamental did once again. So now works on the third harmonic. Fourth harmonic. Now I've expanded the scale here, so I'm only showing, I'm not showing the full half wavelength out there, but you see the same effect. Impedance at the end of the wire is the same as it was. Sixth harmonic. Oh, I don't know why I showed the red line at the 60-degree point. It should be over here at the end. I was trying to show the end fed. That was an error on my part. And of course, at the eighth harmonic, same kind of thing. The impedance at the very end of the wire is that same 2,000 to 3,000 ohm range. So you see, just by happenstance and the way things work out with that voltage and current distribution, now all of a sudden you have one wire that works on multiple bands. I mean, that's a great thing. You don't need traps. You don't need multiple wires. I mean, it just Wow, this is great. So the one tricky part about it is though that you need some way to get that 2,000 to 3,000 ohm impedance down to the point where you can hook a 50 ohm coax up to it and you're going to get some power transfer. And so the way to do that is to come up with an impedance transformer that will do that. So here you see a little diagram of a 49 to 1 balun. Technically, it's an unun, but it and the way that works is you see those twisted wires at the very bottom there. So that's the primary and the secondary of the transformer wires twisted together. And you'll notice there's two turns of that primary going around the toroid donut there. And then the secondary continues, and you see it goes across and up the other side, and you see there's 14 turns of windings in the secondary. So the turns ratio of this transformer is 14 to 2, or 7 to 1 is the turns ratio of the transformer. Now, with transformers, the impedance ratio from the primary to the secondary is the square of the turns ratio. So you take 7 to 1, square it, guess what? You get 49 to 1. So that's how the 49 to 1 transformer works. Very often, a small capacitor is placed across the feed point, and this helps with broadening the frequency response of the transformer and makes it work a little bit better on the higher frequencies. It kind of counteracts some of the mutual inductance of the coils itself, and it makes it work better. Any questions on that? Typically, people use, I think, type 43 or type 31. I think both of those will work.
Greg, the wires all there, they're all insulated single conductor?
Yeah, you would use, typically people use that enameled transformer kind of wire.
Okay.
In fact, I got a picture coming up of the one in a box. You can see it.
Sorry to ask the obvious.
No, that's fine.
I
No,
really
that's a good,
I really wanted to know.
yeah, it's a good question. I'm sorry, go ahead. Yeah. I mean, yeah, I don't remember. Was that on my list? I don't remember. Yeah, yeah. So I'm I'm gonna do an actual model of it, and you can see. But I believe it does resonate. Now there is an issue with, and being a CW operator. When I build an antenna like this, I want it cut for the CW bands. So
Excuse me, Greg, could
Yeah.
you people on Zoom didn't hear the question that was asked, so they did. Then your answer is out of context because
Oh, I'm sorry. So the question that was asked was, is the 12-meter band covered in the antenna? And the answer is yes. There is an issue though with, if you take, for example, the 40-meter one or the 80-meter one, and you cut it for the low end CW, like 3550 or 7040 or whatever, which is where all of us CW ops hang out. If you take that number and you multiply it, times 2, times 3, times 4, times 6, times 8, times whatever, to get to the higher frequencies, by the time just that multiplication, by the time you get up to the higher frequencies, that multiplication puts the higher bands, now you're up in the phone band of those higher bands. So there is some things you can do. You can add a little coil in the wire to add just a slight amount of inductance to bring those higher bands down. That capacitor that we talked about does help a little bit. But that can be an issue. I mean, if you want an antenna that's going to work on all the CW bands, then that can be a little bit of an issue. But there are ways around that by adding a little bit of inductance in the wire itself. Any other questions? So this is what the transformer would look like if you built it and put it in the box. You have a connector, and then you have the post on the side there, which is where you hook the wire to. Now, one of the things that is a little bit different about end-fed half waves is, and I know it took me a long time to think about this, but when you think about an antenna, right, Maxwell's equations tells us in order to get electromagnetic radiation, you need to have current in the wire, right? And so you have this antenna, two pieces of wire, and you hook power up to it either at the end or in the middle, and you get current in the wire. But when you think about it, think about your DC circuits, and things work the same way with RF and AC circuits. But think about your DC circuits, right? The battery and the light bulb. You needed a complete circuit in order to get current to flow, right? So in the antenna, I have a wire and it goes to nowhere, right? How do you get current to flow? Where's the circuit? Well, Maxwell's equations tells us what's going on, but there's something called displacement current, and it happens as part of the electromagnetic radiation of the antenna and the fields. And there's actually coupling between the two wires and coupling between the wires and ground. And that's where the return current comes back to kind of complete the circuit in the antenna so that you get current flow. So there is actually a closed circuit there, but it's not obvious to the casual observer as to how are those wires connected, right? And so one of the things that's even a little bit more funny about the end-fed half wave is, think about it, and don't worry about the transformer right now, but you've got a half wave piece of wire, and you take the coax and you're sort of feeding the center conductor to one end of the wire, and the shield is open. It goes nowhere, right? Well, once again, how do you complete that circuit, right? Well, it's this displacement current again. But what really helps the end-fed half wave to work is if you take that open shield on the coax and you hook another piece of wire to it. They often refer to it as a counterpoise. And it doesn't have to be real long. As usually, rule of thumb, they say about 1/10 of a wavelength at the lowest frequency that you're dealing with. But you need something to have as a path to get that displacement current back and complete the antenna circuit. And that's has a lot to do with the efficiency of the antenna and how well it works. Now, if you don't put anything there, it will still work. What happens is the shield of the coax acts as a way to get that displacement current, a return path to ground. There's another thing that's interesting. I don't know if you've ever thought about it, but I often ask people, and I'll ask the question, how many conductors does coax cable have? Three. Yeah, it's actually three, right? People think, I mean, when you look at it, you say two, center conductor and a shield, right? But because of the RF frequencies that we're dealing with and RF skin effect, current can actually flow in the center conductor It can flow along the inside surface of the shield, but it can also flow on the outside surface of the shield. And it's the current that flows on the outside surface of the shield, if you don't have a separate counterpoise, that acts as the counterpoise and gives you the return path. The problem is that outside current flowing on the outside of your shield is also flowing all the way into your shack, and you're going to get RF. You can get RFI in the shack, and it can cause your computer to do funny things and the radio to do funny things, and all funny things. So you want to try to avoid that. So what people usually do is use the counterpoise wire. That's a much more efficient way for the displacement current to get back to the antenna circuit, and it helps keep the current off the coax. In fact, some people then put an RF choke in the coax up near the feed point of the antenna so that you don't get any of that displacement current on the coax and come back into the shack.
The counterpoise just dead-ended, or
It just yeah. I mean, if you mount the box up at some height, you can just take the counterpoise and just let it hang down vertically. Some people ground it. You can. I don't think you really need to, but I don't think it hurts to ground it either. But okay, so now we're gonna take this antenna that we've been talking about, and I'm going to show you a little bit about actually how it works and what the patterns look like. And the way we're going to do that is through something we call antenna modeling. What is antenna modeling? Well, antenna modeling is a software program that allows you to simulate the antenna, and antenna modeling is a great thing. Before that, how do you know if your antenna worked? Well, you threw a bunch of wire out in the backyard and you tried it, made cute, try to make contacts and stuff. Now you can take the antenna, model it, look at the patterns, look at the gain, look at the impedance, and decide, do I really want to spend time out in the backyard and put one of these up? And so it allows you to look at all the different parameters that we typically look at with an antenna. We can look at the gain, the front to back ratio, if it's a beam kind of antenna, beam width, takeoff angle. We can look at the feed point impedance, so we can see the actual impedance and the SWR. And then we can see all the different plots, the three-dimensional plot, something that's called the azimuth plot, and something that's called the elevation plot. And I'll show you examples of that coming up. Here's what the plots typically look like. The first one is the actual three-dimensional pattern of the antenna itself. If you take that three-dimensional pattern and you took a knife and you did kind of a horizontal slice parallel to the ground, that would give you that azimuth plot. You can think of the azimuth plot as kind of standing above the antenna looking down, and it's kind of your north, south, east, west as to where the energy is going. The elevation plot is if you took that three-dimensional plot now, instead of doing a horizontal slice, you do a vertical slice through that three-dimensional plot. And if you look at the two-dimensional figure of that slice, you see what's called the elevation plot. And you can think of that as sort of like standing on the ground where the antenna is, and it gives you an idea as to what's the takeoff angle, compared to the ground, what angle is that energy going out at? And of course, we all know if you want an antenna that can get long distances, you want a low angle takeoff that gives you that big long hop over the ionosphere. We can also let the software do the impedance plots for us, so we can get a plot of SWR as a function of frequency. And so what we need to do to get this computer program to work, well, we have to create what's called a model of the antenna. And so we actually have to describe in a table to the program the physical dimensions of the antenna, and all that stuff. We have to tell it what, of course, what frequency we're going to analyze it at. We have to tell it height above ground. That's part of the physical layout of the antenna. We can specify what type of conductor it is, wire or tubing, and the types of loss. We can tell it what kind of ground we want to. You can model the antenna in what's called free space, where there's no ground at all. You can model the antenna with what's called perfect ground, is where if you had a metal sheet that went out to infinity in all directions under the antenna, a perfectly conducting surface under the antenna. You can model it that way. And or they have what's called typical ground. So typical earth conductivity, you can do that. If you actually know the parameters of your soil, it's actually a way you can actually put in the conductivity of your soil into the program. But for most cases, you just pick, average soil, and it's good enough for what we're trying to do. And then if you have to, of course, show it where the antenna is being fed, sources. And then if you have any loads or traps or things, you can model those in the antenna as well. And then, of course, the transmission line. So here, this is what we're going to model. We're going to take a half wave wire, and we're going to feed it at the end. We're going to have the 49-to-1 transformer at the end. If you remember back from maybe some of your licensing stuff, but the wavelength of an RF signal is it's calculated by taking the speed of light and dividing it by the frequency. So that's 300 million meters per second divided by the frequency in cycles per second. If you get away from the metric system and convert it down to feet and do it for not a full wavelength, but a half wavelength, it comes out to 492 divided by the frequency in megahertz. But you may think, 492, that's not a familiar number that I remember seeing anywhere. Well, it turns out that the velocity of the RF signal flowing in the wire, that original equation is meant for free space, speed of light in free space. Well, the velocity, the factor of the signal flowing in the wire is not quite the speed of light. It's a little bit less. It has what's called the velocity factor of about 0.95. So if you use that K factor of 0.95 and multiply it by the 492, all of a sudden we get that familiar equation that we've all seen before. 468 divided by the frequency in megahertz gets you the half wave dipole length in feet. And of course, with the end-fed dipole, we need to use that 49-to-1 transformer at the end in order to get a good match to the 50 ohm coax. So in the EZNEC software, the antenna wire is broken up into segments, and the way all of these software programs use a algorithm called NEC, and it stands for Numerical Electromagnetic Code. It was a bunch of software developed many years ago at Lawrence Livermore Laboratories, and it's evolved over the years. These programs that we use what's called the NEC2 algorithm. I think they're up to like NEC4 or 5, and they can just do more and more. But for those, you have to pay for it. NEC2 is free, so that's why we have it here. We don't have to, insulators are not required in the model. Even a half-wave center-fed dipole can be modeled as a single wire. because the source can be placed anywhere into one of those segments. And the NEC2 guideline wants you to break up the wire into at least 10 segments per half a wavelength in order to get good simulation. And so one of the things we have to do is we have to tell the model where our wire is in respect to kind of three-dimensional space and ground. So uses the standard Cartesian coordinate XYZ kind of system, and you describe in a table where N1 of the wire is and where N2 of the wire is. Now in this diagram, I happen to put it so the origin of this XYZ coordinate system goes right through the middle of the wire, but I didn't have to do that. I mean, I could have put one end of the wire at the Z-axis and then go down one of the other axes. It doesn't matter as long as you describe in the program where you've placed the wire. So let's talk a little bit about antennas and antenna gain, and so antenna gain is one of the major factors that we look at when we're looking at or comparing antennas, because it's that antenna gain that takes our signal and gives us more effect, right? More radiation effect. And so in math and antenna things, there's something that is referred to as an isotropic radiator. No such real thing exists in the real world. But what it is, it's if you can think of a source, a point source, infinitesimally small, but energy radiates in all directions equally from that point source. No such thing really exists in the real world, but there are things that approximate it. But the way I like to look at it is, well, think of a lamp and your light bulb. If you take the shade off, right? Well, from an optics point of view, yeah, that's kind of like a isotropic, right? And light energy is going in all directions pretty much. And as with all things in nature and physics and so forth, conservation of energy applies, right? And so the antenna, it's a wire or it's a conductor, right? I mean, it's what's called a passive device. So it's not like an amplifier, right? An amplifier, we feed signal into it. We also supply a bunch of power to the amplifier. And it's all that added power that we're supplying to the amplifier that gets more power out. So what are we talking about when we have this antenna and we're saying we get gain, right? When it's a passive device, we're not supplying extra power to the antenna, we're just feeding energy into it. And so what is that all about? How does the antenna create power to create gain? Well, the antenna gain is just, we're taking that energy, and this is the conservation of energy thing, we're taking that energy from the isotropic radiator that goes in all directions. But what the antenna is doing, it's kind of taking that energy and redistribute it. It's focusing that energy in a particular direction. That's where the gain comes from. And so I like to think about your old-fashioned flashlight. I know they're all LED now, but think about your old-fashioned flashlight that had that little bulb in it, right? You take the flashlight apart, you stick the bulb up. Well, that's kind of like our isotropic radiator, right? Little bulb. It's not very bright, right? And but it's generating energy in all directions pretty much. And now we take and we reassemble the flashlight. We put that bulb in a reflecting cone, and we put a lens on it. We put it all together, and all of a sudden, wow! You turn that flashlight on, and you've got a lot of light, but in a specific direction, right? Well, that's exactly what your antenna does through the antenna pattern, the radiation pattern. It focuses that energy in a particular direction, and that's what gives you the gain. So a lot of times when antennas are being compared, you see the term dBi used, and that's how many dB is this antenna compared to an isotropic radiator? Well, that doesn't really mean anything to me because I don't have a feeling for what an isotropic radiator is. But I do have a kind of a feeling of what a dipole does. So there is often antennas are referenced to what's called DBD, dB above a normal half-wave dipole. Okay, I can kind of relate to that, right? Because I kind of know what a dipole is. And the gain of a dipole compared to a isotropic radiator is 2.15 dB. But you have to caveat of that is free space. You take an actual dipole, some number of feet above ground, in your backyard or whatever, it's actually about 6.5 dBi of gain because you get added gain from the reflection off the ground. That energy that would normally go away from the antenna hits the ground, recombines with the energy going out from the antenna. And so you actually get more gain with a dipole, not in free space, but above ground. The antenna modeling software that I'm going to use, it's something called EZNEC. It was written by Roy W7EL. He did this as a professional business. Roy has since retired from his business, and his website, eznec.com, Roy is actually offering a professional version of his software, version Pro Plus, version 7, free. I mean, this program used to cost a lot of bucks back in the day when, commercial clients licensed it from him and so forth, but he's now letting anyone who wants to use it free. So if you want to try it, go to the website, check it out. You can download it, and it's pretty easy to use. I'll show you an example here. So this is when you bring up the software. This is the kind of the front panel that you see. It's got a bunch of tables kind of in the middle. You see it, the file of the model, and then frequency and wires. That's where you describe the wire in a table, and sources, and then loads and transmission lines, ground, and you actually tell it what kind of wire. So here it says 0, but you would tell it copper or aluminum, depending what you want. And then a lot of the rest of that stuff you could just let default. And then over on the left, there's a bunch of buttons. I'll show you the view antenna model. It can actually show you a picture of what you've told it in the model, and you can look at it and say, yep, that's what I wanted, or no, that doesn't look like what I wanted. Something's wrong, right? And then the button at the bottom, far field plot, that's where it goes and calculates the actual patterns, and it shows you the patterns. And then the SWR is the tab that you push and let it sweep over some frequency range, and it'll show you what the impedance and SWR is as a function of frequency. There's a bunch of other buttons there if you want to take tabular data and actually save it. That's what those other buttons are. So let me let me get out of PowerPoint. I'll load the EZNEC, and we'll see if we can get this to run.
Hey, Greg, you sold me. I downloaded it just to be sure I got a copy.
Okay. Oh yeah, back in the day, yeah. In fact, the real professional ones that he sold to like broadcast stations, and I mean, those are thousands licensing.
I bought it software years ago. And yeah, have three, like, blue.
All right. Out of the way here. See. Let me close a few things out here. Sorry about that. Too many windows. All right. Try that again. Okay. So I think you can see my screen, but in there is the EZNEC front panel. So I've already got the model loaded. You see half-wave end-fed with counterpoise. I've got that file loaded in. And if we do the view antenna, you should be able to see that. So what we have there is a wire, and in this case, I've decided to put the end of the wire right at the origin, and it goes out along the y-axis, some height above ground. And the circle at the end is where I've placed the source. So that's where the feed line would connect. But in this case, I'm just placing a source there to keep the model simple. You could actually connect a feed line and all that stuff, but for what I'm trying to show, which is just the antenna performance, it's just easier to put the source right there at the end. And you'll see next to the green line, the number one, that's wire number one. That's the main antenna itself. And you can maybe see sticking down a little bit below the circle, another green line going down vertically with the number two next to it. That's wire number two. That's the little counterpoise.
Is that some fraction of element one's length or
About a tenth of a wave.
okay. Okay, as you had said, thank you.
Yep. And so, for example, I can show you here's the table. It's called the wires table. And that's where you enter in. You see the first uh, row across there. It says wire number one, and starts out at 0, 0, and 40 feet high, and then it goes out 135 feet along the y-axis and 40 feet high. So we have a 135-foot wire, 40 feet above the ground. And then the other wire is the little counterpoise hanging down. And that looks like that is about 6 feet.
Oh, theoretical. Dipole. You don't have to create a dipole.
It doesn't matter. I mean, I could model the sag in there, but you'd never see the difference in the pattern. Very, very, very minor difference. But you can model it if you want. And you can model inverted V or however you want. And of course, the zoom window is in the way. All right, so let's, I'm going to hit, well, other things here. You see I have a real ground selected. I have copper wire. My units are in feet. I don't have any loads or transmission lines. I have just the one source. And initially, I'm going to look at, even though this is a 80 meter fundamental, I'm just going to look at it at 7 megahertz. So I'm going to tell it to do the far field plot. You go off and do some calculations, and that's what the three-dimensional pattern of the antenna looks like at 7 megahertz. If I go over here and I click this little thing that says azimuth slice, it does a horizontal slice through that three-dimensional pattern at the maximum gain point. And if I take that slice and say show the two-dimensional pattern for that slice, then this is what you get. I think that should be familiar to everybody. For a half-wave dipole, you get that nice figure 8 pattern. The wire is going along the center there, and the maximum radiation is broadside to the wire. Look over on the left here, and it says the maximum gain is 7.13 dBi. If we now go back and look at the three-dimensional pattern again, but this time we look at the elevation slice. We do a kind of a vertical slice through that three-dimensional pattern. And we now show the two-dimensional plot of that. Here you see what's called the elevation plot, or the takeoff angle. And you'll see it is skewed a little bit. It's not totally symmetrical, and that's because we're feeding it at the end of the wire. But you see the maximum gain point on that where the green dot is, and then it looks like elevation is 55 degrees takeoff angle. If you raise the antenna higher up, that takeoff angle would come down lower. At 40 feet, we're not even a half a wavelength on 7 megahertz. In order to get the takeoff angle lower, you have to be at least a half a wavelength above the ground, and it gets better as you get closer to a wavelength above the ground. All right, now let's take a look at the SWR. So I'm telling this to start at 3 megahertz and go out to 30 megahertz at a tenth of a megahertz increments. And so we'll let that run. It does take a few seconds here for that to run, but now it's going off and doing all those calculations. And when it's done, it'll come back with a plot that we can look at. Almost done.
It's a big spectrum, Greg.
Yeah, I swept the whole HF spectrum. So, okay, so now you see a plot of the SWR as a function of frequency, and you say, oh my God, that looks awful. Terrible. All right. So what didn't we do in the model? We didn't put the 49 to 1 transformer in the model, right? Now I could have installed in the model, there is a transformer thing. You can actually put that in there. And so I could have put a transformer with a, 7-to-1 turns ratio in there and done that. But there's actually an easier, quicker way to do it. And you'll notice over on the very left hand, this is looking at the antenna from a 50 ohms uh, uh, kind of eye thing. But you see in there, I put in an alternate impedance of 2,450 ohms, which happens to be 49 times 50. That's where that 2,450 ohms. So if I go in there now and I check that box for the 2,450 ohm reference impedance, it will show you the same action as the 49-to-1 transformer would do for you. And you'll see what the 50 ohm coax would actually see on the other side of that 49-to-1 transformer. Well, I think that looks a little better. So there you see the multiple harmonics of the antenna and how it's working. Just about on every band, you see the SWR is like, below 2-to-1, even 1.5-to-1. So, and you can take the little cursor here, and here's your 80 meter resonance. That's a little low, 3.4 megahertz. So you adjust the length of the wire to get these resonances to fit in. I just took 135 feet as kind of a an average number, but you see all the other bands here. This will be 40 meters, and of course this will be 10 meters. Whoops. And like I said, 29.3, it's up on the high side, but someone was asking about, so here's this would be 12-meter band. So that is high. You would definitely need that inductor in there to bring that in, because I think it's what, 24 megahertz is where the 12-meter band really is. Yep. Yeah, I didn't do that, but yeah, you could model the inductor, and it has a field in there for inductors. You can put it, you tell it what segment you want to put it in, and what the amount of inductive reactance is what you actually tell it in the model. And yeah, I can model that. I didn't do that in this case, but yeah. Any questions about any of that?
What does the pattern, I'll call it the far field plot look like on some of the harmonics?
I can show that. It's going to be very spiky, of course. You've got a multiple wavelength antenna at that point. But let's look at it. For example, on let's do 21 megahertz, for example.
I believe the mics are out on the table. If there are questions in the room, make sure you grab one of the mics, because the people online, they hear dead air when we're asking questions in the room. So,
yeah, so the question was, what does the antenna pattern look like at higher frequencies? So here's the pattern at 15 meters. And like any long antenna, on 15 meters, this wire is multiple wavelengths long. So the antenna is kind of spiky. But the good thing is you get some gain out of that extra wavelengths of wire. So if we look at the azimuth pattern here, it's very spiky, but we're seeing, almost 11 dBi of gain in some of the peaks of where those spikes are. So that's not bad. If you're trying to talk to somebody who's in one of the nulls, then yeah, that could be an issue. But if he happens to be in one of the peaks, then good. But this is very typical of a longer multi-wavelength wire on a higher frequency. This is exactly what the pattern looks like. I'm sorry, you had a question, Gil? Certainly less than a half a dB, usually a few tenths of a dB. It's very minor. The transformers, if you use good quality core material and wind it properly with the right size wires, the losses are very, very low. Oh, I'm sorry. The question that Gil asked, I'm sorry, was how much loss would you expect to see in the 49-to-1 balun? Should be very, very low.
How much power can that 41 onion do?
Depends on how you make it. What
Say the one that you showed there, the picture.
probably 100 watts. Yeah, if you want a kilowatt, you're going to need. You would probably stack multiple cores, and of course use heavier wire, and sometimes they wrap them in like Teflon tape just to increase the breakdown voltage of the core and everything. But that one that I showed is probably good for 100 watts. They make little QRP ones, which are really, tiny, that'll handle like 5 or 10 watts.
Did you actually try this antenna on the air?
I have not tried it myself, but I've been with people doing POTA, and I know a lot of people who I teach a number of classes for the Long Island CW Club, and a lot of the people I talk to on Zoom as part of that club are all using this antenna and have nothing but great things to say about it. But it's a half-wave dipole. I mean, it's not going to perform like a Yagi or whatever, but boy, with a single piece of wire and you get all those bands, kind of hard to beat.
How much trouble have your friends had with RFI back into the shack?
Um, that can be an issue because, as you can see, I mean, the one nice thing about a center-fed dipole is it's a very symmetrical antenna, right? Everything is nicely balanced. You got half a wire on each side. Everything is nicely balanced. You don't tend to get stray stuff because it's a very, symmetrical, balanced system. End-fed antenna is not balanced at all, obviously, because you got, like I said earlier, you've got the semiconductor, your feed going to kind of one side of the wire and nothing connected to the other side other than your counterpart. It's a very unbalanced system. So that can be a problem. What people have found, if you use the counterpoise method, that really helps keep the currents off of the feed line. But if feed line, current on the feed line is a problem, you can install a one-to-one choke. It's essentially just take one of those toroids and wrap a bunch of coax through the toroid. That acts as a one-to-one common mode choke, and that will kill a lot of the current trying to flow on the outside of that coax shield. Any other questions? Okay, I think that's it. Thank you.
Thank you, Greg.
Nice job, Greg.
Thanks.
Say goodnight, George.
Good night, George. November 20th, next meeting.
Okay. Next meeting is gonna be November 20th. That is the third Thursday, not Thanksgiving. Thanksgiving will be the 27th. Our meeting is November 20th. Also, this is the time when we need to open it up for nominations for officers and board. So if,
Hey, Greg.
you know anyone who would like to,
I was running some numbers, and you can get a couple of KV.
Yeah,
across-
hey, without a mic, Dan, they don't know you're talking.
Nah.
Without a mic, the Zoom people don't know you're talking. Well,
The one right.
somebody hand them a mic. There we go.
he lives here now.
Okay, our next meeting is going to be November 20th, which is the week before Thanksgiving, not the week of Thanksgiving. So we will be here. Also, this is the month when we open it up for nominations for officers and board. We will be taking nomination names next month. So if you would like to run for a position, if you'd like to run for one of the open positions like secretary, or maybe even secretary, maybe you'd like to be a secretary, or any other thing, we'd like to know. So you can send those to me through the Dan Rouse 6 at Yahoo, which you see on your when you get the club notices and stuff. So and then next month we will be announcing the nominations. Maybe when do we poll the existing people to see if they want to run? Just before? Okay. Okay.
Sorry, Mike. I think you had a comment or something.
Mike, BNC, did you have a comment or a question? You just muted yourself.
I'll catch you later with that.
Okay.
All right. That's a wrap then.
Da 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 da.
Yeah. Hey, one last thing for the people in the room. Excuse me. Hey, one last thing for the people in the room. We could use some help with tables and chairs, please. Thank you.
There's going to be also, if you're going to help out, there's going to be a funeral reception tomorrow. So we just need to stack the chairs and the two long tables against that